Yeah, when I was asked to do this, I was like, oh, okay, I'll just be sitting at my computer, making a model, running simulations. I did not expect that we would get the contacts to come up and actually do a modal analysis on a replica of the Liberty Bell. So it was like a field trip. You come up to a test with your friends, it's fun.
Why not, right? It's the 250th anniversary. It's a piece of American iconography.
It's just fun, right? Getting to tap on the history and understand its response. Modal testing happens throughout engineering. It's linked to acoustics to try to understand the vibrating properties of structures and how they radiate noise.
Modal analysis is the measurement of vibration modes of a system. If you've ever been on an airplane, you've probably seen the wings bend up and down a little bit, or if you've been at a traffic light when it's really windy outside, you've probably seen the traffic light bump up and down. So those are the modes of vibration of structures. Along with that, there are frequencies where those vibration shapes happen, and those frequencies are what you hear. So when the bell is making this nice, pretty sound, each one of those frequencies that you hear is actually a vibration shape that's pushing on the air outside and getting that vibration to your ear.
ARL is really one of the leaders in modal testing in the country. This is a nice open way to highlight that technical capability.
When John was first asked to do this, make a model of Liberty Bell, John went to Google, said, give me the dimensions of Liberty Bell, and it gave him very obscure numbers.
First things first, I need geometry. I need to have the shape of the bell so that I can make a model and predict what the Liberty Bell would have sounded like when it was ringing in the Pennsylvania State House 200 years ago. The original Liberty Bell was made in 1751, and it took about a year for it to be made and then shipped across the Atlantic to arrive in Philadelphia. And then they hung up the bell in the Pennsylvania State House and they went to ring it. And the first time they hit it, it cracked immediately. They're, running around with their heads cut off. We need a bell for the Pennsylvania State House. So what they did was they contacted a local metal founder.
A couple folks, John Stowe and Pass, are they both John Stowe? So a couple folks, Pass and Stowe, made other metallurgy things, made pots, pans, things like that, and they were like, hey, we'll give a shot at casting this bell. So they recast it, brought it out in front of all the townsfolk. They rang it, apparently it sounded terrible.
And at the time, John Pass and John Stowe, they had not made any metal cast object as big as a bell. This bell weighs like 2,000 pounds. The heaviest thing that they had cast was like 10, 20, 30 pounds, something like that.
And so they took the bell, they melted it back down, they threw in a bunch of random stuff like lead, silver, arsenic, and then cast it for the third time. I guess that's the one that stuck. So it rang for like 100 years or so. And all of a sudden it had this giant crack in it.
I will say that it wasn't tuned like normal bells. Bells are really interesting acoustically. The first 5 frequencies of the bell are tuned to be very specific ratios of each other. So the first note is called the hum note, and that is the lowest note of the bell. It kind of rumbles, it's the base of the bell, and that's half of the fundamental. The fundamental is the pitch that you hear. So if you hear a bell and it's ringing at like an E4, that would be the fundamental note. Then there's the tierce above that, that's a minor third above the fundamental, followed by the quint, perfect fifth above the fundamental, and then a full octave above that is the nominal, and that helps add brightness to the sound. The Liberty Bell is a type of English church bell. If you listen to any church bells that were made post 1890, if you have a good ear, you'll be able to hear those notes. The Liberty Bell was made before that, and it was actually made in a period of time when they had forgotten how to tune bells that way. The guys who knew how to tune bells that way died, and then nobody else knew how to do it. So from like 1680 to 1890, they only tuned the fundamental. So they were like, if we want this bell to ring at like an E4, we're going to tune the fundamental to an E4, and then the other 4 frequencies, just whatever they are, they are. And the effect that has is it kind of muddies up the sound a little bit.
It's a whole art form that apparently died out for hundreds of years because people didn't want to share their secret.
So because this was made by not a bell founder, The ratios of the first 5 frequencies, they're not exactly what they are for like a quote-unquote perfectly tuned bell. In order to tune a bell, what they do is they'll carve out metal on the inner surface of the bell to change the thickness of the bell, and that'll change the sound that the bell makes.
And that actually became an interesting part of all of this because we're trying to make this model of the bell, and it turned out all these replicas sounded a little bit different. I did some processing, some analysis of the bells, and it turns out the first frequency is kind of close. And then we really went into this deep rabbit hole of once you get past the first frequency, once you try and start tuning it to make it sound nice.
If you're not a bell founder and you don't know how to do that, you're gonna cast the bell, and then as cast, you're just gonna say, here's your bell.
It became very obvious very quickly that this was a very sensitive structure, that getting the right dimensions was very important. The CAV, the Center for Acoustics and Vibrations, tested a replica of the Liberty Bell. Where is that bell? John went digging and found that it was at Penn State Behrend. The Penn State Behrend people blew it out of the park, and they did a full 3D scan. From that 3D scan, John could make the actual cross-section of that Liberty Bell replica.
So scanning the bell itself is a very time-consuming process. As tall as it is, as high as it is, and then getting inside the bell underneath, as well as placing different markers on it so that the scanner can piece it back together later.
It's the Liberty Bell. What's not to be excited about it? I mean, we're in Pennsylvania after all. It was a little unique. We were worried about the reflectivity of the metal. The way the scanning works is it's basically, it needs to maintain tracking of where it's at. We were worried that the sheen would be too uniform throughout, that it would lose tracking of what it looks like. But you can see that there's a lot of markings of just wear and probably people touching it and whatnot. So that actually worked out to our benefit because these random, what I'm guessing are finger marks, actually gave us unique tracking places so that the software was able to really maintain its location in space and time in a way that gave us a really high fidelity scan.
I think it's great that when John Young called to say, could we come up and scan this, I knew that we had Professor Shelton's lab to go through, and without even thinking, his first instinct was to call an undergraduate student to do that for him.
It is a big part of this building and a big part of Pennsylvania history, so it kind of makes it more interesting than just scanning everyday objects. It's something that's worth preserving and nice to give access to other people.
They provided a very, very fine mesh of the outer surface of the bell. And what we can do with that is basically cut it in half and we get a cross section. Since the bell is just a revolution of a cross section, we can mesh basically the thickness profile of the bell and then revolve it. We're breaking up the bell into a bunch of little cubes, and then we're solving equations on these cubes to predict how it's going to vibrate. Typically, when we make these numerical models, we want to have some experimental backing for it, like something to validate it.
Yeah, so John sent a really lengthy email saying, hi, I want to do modal analysis, which I think they read as, I'm going to hit your bell with a hammer. And they graciously let us come up and we did a full modal analysis.
From modal analysis, we get the natural frequencies of the structure, the mode shapes of the structure, how it's deforming, and then the loss factors, so how it is dissipating energy at each of those frequencies. And then we have some more confidence in the noise that we're predicting from our numerical model. When we start doing a modal analysis, one of the first things we need to do is figure out where we want to get data from.
If you hit the bell along its rim, sort of where the striker actually would be, versus if you hit it in the middle or if you hit it at the top, you're going to get very different sounds. All of those frequencies are still going to kind of be there because they're all going to get excited, but they're going to get excited in different proportions. In order to actually model that or capture it accurately, you need to sort of account for all possible combinations of forcing. You need to say, okay, can I measure all the ways that the structure might actually be excited? And so modal analysis is a very clean and very standard way to get at those.
So when we arrive, we bring all our equipment with us. We bring accelerometers, which measure vibrations, hammers, which have sensors built into them so they can measure the force delivered to an object. And we begin by instrumenting the object. So we'll put some tape on the structure to protect it from the adhesive we use to stick on the sensors. and then we'll stick on the sensors with super glue. So you set up the sensors, mark out all the points you're going to hit.
One of the beauties of acoustics is this idea of reciprocity, where if you excite a structure and measure two different places, it's the same as if you excited where you measured and measured where you excited. So what we can do instead of instrumenting everywhere and hitting a few places is hit everywhere and instrument a few places. So we had 7 rings going up the bell, so we just put an Excel on every ring to make sure we didn't miss anything.
Then you begin testing, and all that consists of is just hitting the bell and letting it ring until we're done collecting data. In this case, I think we had somewhere between 80 and 90 points that we hit, because we want to characterize the vibrations of the surface of the bell all around the bell. For every point, we'll hit multiple times and then average that data to get a smoother signal.
You take that data, extract the frequencies, mode shapes, and loss factors, and then it's a matter of visualization.
So you can't see the bell vibrating with your own eyes, but the sensors are sensitive enough that they can pick up the displacements as the bell deforms when it's vibrating. We can actually animate the bell as it would be vibrating at that frequency.
We have the first 5 frequencies of the bell that we measured, and at each one of these frequencies, the bell is moving in a very specific way. So if we look over here, you can see for the hum note, kind of the full body of the bell is moving. And then if we go to the fundamental, the body and the lip of the bell are moving but out of phase with each other. We go up to the tierce, it's kind of just the lip that's moving now. The quint, really the body of the bell it's moving, the lip is not moving very, very much. And then lastly, the nominal, where it's again, mostly just the lip moving, generating all of the sound at this frequency.
And those things all go into comparing to the model that John's created. John's model has its own frequencies and mode shapes, which are hopefully similar, but if they're not, we can use the data and the model together, update the model to make it more accurate, and think about the physics that's governing the differences between the two things.
So probably the biggest challenge that we had was making the model and getting the model to actually compare to the experiment well. Becoming more of a psychoacoustic effect than I think we really realized. It really sent us down a rabbit hole, and that I don't think we've still quite figured out. It's not just getting the physics right, it's not just getting the structure right, but there's a receiver in the loop, and we're the receivers, and our brains do wacky things with acoustics.
Your ear can hear frequencies up to about 20 kilohertz or 20,000 hertz. Right after you hit the bell, you're exciting frequencies that go up to 15 or 16 kilohertz. And even though those frequencies are only around for, a fraction of a second, your ear can still hear them. The higher you go in frequency, the worse at predicting frequencies your model is. So you might be able to get the first 5, 10, 20, maybe 50 natural frequencies of your model to match within like 1% of the bell. But when you start getting higher, those differences become bigger. You start seeing 2, 3, 4, 5% differences. And your ear recognizes that as a completely different note.
So as frequencies get higher and higher, their wavelengths or the vibration patterns get smaller, they get tighter. And so really low frequencies, they're not going to care about a small imperfection in the bell, or they're not going to care about maybe a small defect in the cast where it's maybe a little thinner than it should be. When you get to really high frequency, those little defects start to matter. The fact that John's model was probably the most correct model of a bell that has existed so far, and it still doesn't match quite so well at high frequency, is a testament to how difficult it can be. You can spend your entire life trying to capture all these things and probably only gain so much. It's just a reflection of the realities of life and how far the science has come. It's very, very good, but it's never quite good enough to fully capture reality. At the end of the day, it sounds like a bell. It has the right pitches at the low frequency. It's just that color, that timbre, that's just a little bit different at the high frequency.
Acoustics research is important because it impacts everything. Right, there's nothing that doesn't have acoustics. Understanding sound and an impact on the human is important. That's acoustics. Understanding the susceptibility of undersea platforms is important for defense. Acoustics is also a fun challenge. It's difficult to understand how to do noise control, signal analysis, so it can be a fun avenue to solve hard problems.
What we've done here is really relevant to things we do every day. We do the same operations we did on the Liberty Bell with parts that would go on submarines. And it's also just a a lot of fun to take something seemingly simple and get granular about the physics that's behind it.
It really shows the power of Penn State, being able to stretch all the way from an undergraduate education and make an impact all the way through fundamental research.
Penn State has a wonderful degree program in acoustics. It's certainly the only place in the United States where you can get an actual degree with acoustics on your diploma. Oftentimes, those other places that study acoustics or vibrations, they're very niche. They study a particular part of acoustics, whereas Penn State really tries to give you a very broad exposure to all different flavors of acoustics, and how the world interacts from these small vibrations on a structure to the things that you finally perceive in your ear. So the psychoacoustics aspect, how do we perceive the sound? Why does our brain do that weird nonlinear acoustics thing? All of these are covered in the Penn State Graduate Program of Acoustics, which I think makes it a really nice, holistic graduate program if acoustics is if it's your jam.
It's amazing to me that the guys in the 1600s, Peter and Francois Hemeny, these were the guys that like learned how to tune the first 5 partials of a bell. And they did it in like the 1600s. This is before electricity. Like, that's insane. They knew about how to tune a bell and get it to vibrate just right so that it sounds perfect.
Truthfully, my favorite part was we spent all day testing this bell. We heard the same sound for like 6 hours straight, every minute for 6 hours. And I thought we would get in the car and we would like not speak to each other for the rest of the day. And we got back, we sat down and started pulling up sounds on YouTube and trying to recreate the bell sound and being like, is that what we listened to all day? We were pulling up results from papers. At the end of the day, we just really love acoustics and we wanted to see what it looked like.